Hello everyone, this is video 11.2. We're going to be looking at length, area, volume, and dimension. There's a lot of overlap between 11.1 and 11.2, but there's enough stuff that makes it different that's still very much worth your time to watch and take notes on. But if you haven't had a chance to watch 11.1 yet, then you may want to go back and review that material before we get started. So let's get going. So some more definitions here, and again, a lot of these definitions look very similar and may even be repeated from 11.1. So this it's not new potentially, but still very much worth going over. So the length, which we talked about in 11.1, the size of an object that is one dimensional measured along that one dimension. Now, if you have something that its one dimension is height, then we're still going to call that length, which I know is a little confusing. But anytime you have something that is one dimensional, when we measure along that one dimension, we're still going to call it the length, even if it's oriented to where it may look like width or may look like height. So if your one dimensional object is going, let me get the pen going here. If it's going up and down like this, I mean, this looks like height because it's going up and down, so we would think of it normally as height, but we're just going to call this generically the length. So we're just measuring along that one dimension. So if we were to say this is 3 centimeters, we could call it the height being 3 centimeters if it was part of a 2 or 3 dimensional object, but generically, like I said, we're just going to refer this as the length. By one dimensional, we just mean that it's only going to be moving in this one direction, in this case, sort of up, down. There's no left, right. There's no front, back. It's just moving in that one direction. And so that's what we mean by a one-dimensional object. One of the things we're going to look at later on in this section is this idea of perimeter. And so if I have a rectangle here, and let's say this is 6 by 4 inches, then the perimeter is going to be this length around the rectangle. Now, you may get some students who are a little confused by this because we're talking about this as being one dimensional. They're going to want it to be sort of moving in this one direction. And so if I go from here up to here and then change directions, well, now, isn't this a two-dimensional object? Well, yes, the object is two-dimensional, but what we could do if a student is confused by this is take all of these sides and lay them out, moving around this way, we could lay them out along one dimension, like this. So we could see how, even though the object is two-dimensional, the thing that I'm measuring is measured along one dimension. So when I go up this 4 and over this 6, I'm still measuring linearly along the edge of this shape. I'm not measuring across the shape like that. And even if I did, that's still a straight line. That's still being measured along that one dimension. So if it helps some students for you to take the characteristic of this two-dimensional shape and lay it out in one dimension, like down here, to show how that perimeter can be measured along a line. If students need that, then certainly show them that so it makes more sense. Moving on to two dimensions. So now a two-dimensional object we mentioned in the previous slide has two different directions, and the book doesn't really talk about this, but it is pretty important to discuss that these directions are always at right angles to each other. So, if I have something that sort of moves like this, and this is some acute angle here, these are not going to be dimensions. They need to be at a right angle to each other. And so that's why in the previous slide I used this rectangle, because these two dimensions are at right angles to each other. So when we look for the amount of surface that is taken up by a two-dimensional object, we call that the area. So generally the size of the two-dimensional object. We can also talk about this as the surface area. And so generally when we're talking about surface area, we're talking about a three-dimensional object like a cube. So we'll draw a cube real quick here. And so all of these are surfaces of the cube. And so we're not measuring linearly along this edge. we're not measuring the volume inside the cube. We're measuring this two-dimensional aspect here, what's on the surface of this cube. And again, we can think of now this two-dimensional surface and this two-dimensional surface over here. And likewise, if students get confused by that, we can lay all these surfaces out into what's called a net and show all of these sides in a plane and measure all of these areas, or whichever areas we need this way. So if students are confused by the two-dimensional aspect of a three-dimensional object, we can flatten that thing out. And now it's no longer three-dimensional. By flattening it out like this and putting all the surfaces in a plane, we see it now a little bit more clearly as a two-dimensional object. Again, two-dimensional, like I said, we need to have these things going in two different directions that are right angles to each other. This here has length and width, however you want to call it, but because it's flat, it would not have any height to it, as opposed to this cube, which has length and width and height. It has all three dimensions, which we'll talk a little bit more about on the next slide. I want to point out that if this were, like on the previous slide, if this were 6 centimeters and 4 centimeters, then my area now would be 24 centimeters squared. And if you want to think of that as breaking it into this rectangular array and then counting all of those squares, certainly could, but like we talked about in section 11.1, we want to make sure we break this into squares that are 1 centimeter by 1 centimeter or 1 square centimeter. So a lot of times we'll see these units having the square in the units. But I just want to point out that there are units of area that don't have that square. And so even though this is very often the case, it's not always the case. An acre of land, for example, is a measure of area, but does not use anything squared. There's nothing squared in the explicitly in the name, although it's measuring a square area. So the book kind of talks about these units of area saying something squared or showing this second dimension. And it's often the case, but it's just not always the case. So now we can get into this three-dimensional object. So we've talked about this cube already. So we'll draw another cube here, and we'll call this 4 inches by 4 inches by 4 inches. And so we have 3 dimensions now, and we can see we've got our height here, we've got our width here, and we have our length here. And it's relatively arbitrary because if I don't like the way these are oriented, I could always rotate the cube and make the length and the width switch up. I mean, it's a cube, so it doesn't make it, the numbers don't change. But if I did have a rectangular prism like this, that's a terrible looking line there. So if this were 2 by 3 by, let's say, 5, for example, and we'll go back to centimeters for no real reason. So here, the way that this rectangular prism is oriented, I've got my height here, I've got my width here, and I've got my length here. But the point is, like I said, this is arbitrary. I could rotate this prism. I could stand it up like this. And so now my height would be the 5, because this we can see it's the longest one here. And so, the labeling of these things ultimately doesn't matter. But we want to be consistent to the drawing. If I draw it so the height is 5, or if I draw it so the height is 2, I want to make sure I label it in a way that's consistent so students can understand what's going on. These 3 dimensions, again, they need to be at right angles to each other. So I can see I've got my width and my height here. They form a right angle. And then this gets a little confusing because we can see here that here's the height and here's the length. But in order to draw this 3-dimensional object as a 2-dimensional projection, this right angle looks a little distorted. It looks obtuse. So it can be a little bit confusing. Most students will be able to understand and sort of follow what's going on here, but it can be a little bit hard to really see at first how these things are all in 3 dimensions. So I wanted to show this little picture here. Now, don't worry at all about the right hand rule for cross products. That's kind of not the point of it. The point is the way that those fingers and that thumb are held. And so if a lot of times the problem is students are thinking about these right angles in two dimensions. They've seen rectangles, they've seen squares, and so they understand how two lines in a plane can form right angles. But now, how three lines or rays or line segments or whatever can form right angles in space can be a little confusing. So, by taking that index finger and sticking it straight out, and then putting your thumb straight up, and then the middle finger there kind of comes off at a right angle to the hand and to the index finger. And so now you're no longer looking at this on a plane, you're looking at this in space, and you can rotate your hand to check to see that everything is, in fact, at a right angle to each other. And so you can even see here in the picture, uh, like we're talking about here, this is a right angle, but because we're having to draw this on a flat surface on a plane, that right angle is really hard to see. It's really hard to understand, and intuitively, students are going to look at this and think this is some obtuse angle, even though it's not. So by getting students to kind of like form this, right hand rule thing with their hand, and see the way that all these angles are formed in a space, they can see how three objects, three lines, can make three right angles in a space like this. So don't worry about the cross product, what that means. It's something to do with linear algebra, so you don't need to bother with that. But it's the diagram of the hand, and being and students being able to put their thumb and fingers like that so they can see how the right angles are formed, or maybe even so you can see how the right angles are formed. So our checkpoint problem: does every rectangle with the same perimeter have the same area? So, I'll let you take a guess at that first. And then after you've had a guess, uh, draw a few different rectangles with a perimeter of 24 centimeters. So, there's more than one rectangle. There's even more than one using just integer sides. So I'll let you kind of work through two, three, four different rectangles that have that perimeter. Now, find the area of all those rectangles. Did you always get the same area? So did the same perimeter seem to indicate that all those rectangles have the same area? And then if they don't have the same area, what do you guess is true about the rectangles that have the larger area or the smaller area? Is there any sort of tendency that you notice? Is there any sort of hypothesis that you could make about what's true about those rectangles? So I'll leave you to think about that question. As always, if you have any question about that or anything else from the video or from the homework or anything else, please bring your questions to class and we'll get them answered. All right, thanks.